All right, so here we are. Oh yeah, thank you for that. Permutations and combinations. Some of you might remember some of this from um, Algebra 2. It is talked about there a bit. Let me get my glasses in on this. All right, a combination sometimes they're written this way. I've also seen them written like this. I think the lower two are more often used in the United States, whereas the upper two are more often used in Europe. But the uh, the idea is the same. N is the number of items that you have to pick from, and K is the number of items you can pick. So think about it as, you have 30 people in a class, and I have to pick 5 of you to do an errand, or something like that. Um, so number of items, number of choices. Now, which one is bigger, combination or permutation? No, not of N or K, but if I have if I say I have 5 items and I can choose 3, is a combination, the number of combinations, going to be bigger or smaller than the number of permutations? Who? It's not about repetition. Okay, how about this? Um, okay, 3 people sitting at a table. Okay, I can number them 1, 2, 3, or I can number them 3, 2, 1, or 1, 3, 2, or 1, and so on and so forth. Permutation is when you move them. Okay, a combination just says, here are all of the items in the bag. Okay, for example, if I say I have 5 items and I can choose 3. Okay, let's call them A, B, C, D, and E. If I can choose 3, let's start picking some. We went through this the other day, right? Okay. If all I cared about were combinations, like the example that we did the other day was you go up to a buffet and you pick 3 items off of the buffet. Well, you're just going to sit down and eat them. You don't care which one you picked up first, right? Because you're just looking at your tray and you're saying, all right, I got mashed potatoes, string beans, and meatloaf. Okay? But to some situations, is it mashed potatoes, green beans, and meatloaf, or is it meatloaf, mashed potatoes, and green beans? One of them, the order matters, and the other one, it doesn't. In a combination, this is a grouping. It's just a collection of things. But in a permutation, you're scrambling them. Okay, this is not the same as BAC or BCA. Okay, or CAB or CBA or ACB. You see, in a permutation, these are all different items. Okay, but in a combination, we don't care what the order is. Okay. So in a permutation, order matters. In a combination, don't care about the order. okay? So Jack and Jill doesn't matter in a combination, but Jack and Jill could become Jill and Jack in a permutation, okay? All right. Well, mathematically, let's see if we can figure out a way to look at this. Now, in a combination of C n choose k, this is n factorial, well, actually, it's the binomial coefficient. We're going to leave it there. This is n choose k. And, of course, you remember this. And I'm sorry about the video, the audio kicked out on me. Yeah, sorry, but you got the notes. Okay, good. All right, now in a permutation, we have a term missing. This is that. Basically, one of them has an extra term in its denominator, and the other one doesn't. And if you think about that for a minute, that kind of helps you out. Because in a combination, ABC is kind of like the all-encompassing answer for ABC, CB, AB, CB, CAB, and all of those others, right? Permutations, there are more permutations of things, okay, because I can swap them around, right? Well, if I can swap them around, I'm going to have more answers. Does that make sense? I'm going to have larger numbers of things because now all of a sudden I can get another answer by just changing numbers around, all right? This guy has a bigger denominator, which means its value is going to be smaller. There will be less combinations than permutations. Also, you can see that right here. We're multiplying by a number. It's a bigger number, okay? All right. So let's see about how many words how many words can I make from the word word? Get it? How many did you get? What? Sitting around idle? Bumping a log? Waiting for the math to be pulled out of the ether? And don't sit there and compute them all. You'll be here for a little while. Hmm? So DRWO is a word, right? Well, how many do I have? I have how many items? And that's my N. How many can I choose? The word that I make, I should, yes.
I have NHS lists.
Okay, thank you. Somebody remind me about these. Now, if I'm choosing 4-letter words, okay, then I would have 4 choices. If I was choosing 3-letter words, then K would be 3. 2-letter words or 1-letter words, right? If I just said, how many can I make? It would be all of the 4 letters, all of the 3 letters, all of the 2 letters, and all of the 1 letters. Okay? So you would actually have to compute 4 different things and add them all up. Does that make sense? Does that fly? Okay. So let's try 4-letter words out of those 4 choices. So it's 4, choose 4. Okay? Am I looking for a permutation or a combination? This is a permutation because order definitely matters. All right? So if I'm doing P4, that's 4 factorial over 4 minus 4 factorial. Right? So 24 items. Now, when K is 3, now we have 4 factorial and again we wind up with 24. We can see this, and actually let's go through the 2 and the 1 case for completion's sake. Four times 3 times 2, and then we cancel out the 2. All right, now let's just see that this actually really has a grounding in reality. Okay. If I'm doing the case of 4 words, 4-letter words, there are 4 choices for the first letter, 3 choices for the second, 2 choices for that one, and now I'm left with only 1. Okay? So 4 times 3 times 2 times 1 gives me 24. Here, I still have 4 choices for my first letter, 3 choices for the second, and 2 choices for the last one. See, the last one, that 1 in the 4 choices, that was predetermined the second I get that third space, because now I've only got 1 left, right? So now this is why we still have 24 items. If I have 2, and we would add all of that up, okay? And come up with 64. Okay? So there is a real rational basis behind all of this stuff. Okay? Let's try something a little bit different. Let me forget those. All right. This is a good question. It's when you start throwing in restrictions that all of a sudden things get goofy. All right? But just for giggles, let's see, let me give you another one like this. Is that coming along? Do we get it? Sorry? So what do we have? We have 7-letter word, choose 5. So we have I get 21. No, way wrong. Let's, So it's permutations 7, choose 5, right? So this is 7 factorial all over 2 factorial, right? I was doing combinations for some reason, right? We good? So this is 7 times 6 times 5 times 4 times 3, right? Wonderful. 20, 120, and now 21 times 12, 20, 21 times 12, so 2, 2, 4, 5, 252, 25, 20. It's a lot of words. And I will not give you anti-disestablishmentarianism. I promise. Anti-disestablishmentarianism? Mono-ultramicroscopic silicovolcanoconiosis?
That's a word.
Yeah, it is. Oh, right, because I didn't say how many words I wanted. How many letters I wanted in my word. You see, I could have 4-letter words, 3-letter words, 2-letter words, 1-letter words. But this time I'm saying just 5-letter words. Question? Anti-disestablishmentarianism? It's the resistance to the abolition of church and state. Yes. How did I get 21 times 12? Because I did 20, 5 times 4, and then I did times 6, that gave me 120, times 21. I did 12 and then 21. I don't want to erase it over here. Good enough. All right. Now, did some of us get that number? Some of us? Any of us? 1 or 2 of us? Yes, we got it? Great, wonderful. Now, let's say, here's where you live. Here's where you work. And here's the store that you want to visit. Okay? There are 3 roads that get you from the store, your home to the store. And there are 2 roads that you can take from the store to your work. I'll just change my letter here. Home. Phone home. All right, so how many different ways can I make the journey from H to W? 6, right? I can take any one of 3, and then I have to take any one of 2. So it's 3 times 2. But what if I did this? What if you found a shortcut? now how many ways? 7. So that was added to my total, right? So what if I gave you something like this? This is the beginning of what is called graph theory, okay, which is another form of mathematics that's really kind of cool. All right, so let's figure out this evil beast, shall we? Let's take it one branch at a time. Let's take the upper branch. How many different ways does that upper branch represent? No, just the upper branch. From home to the library to the market to work. How many ways can I go through that path? 3 different ways. All right, from home to your friend's house to the bookstore to work. 6. And this last branch, from home to the cleaners to the pet store, running out of letters, to the zoo, and then to work. Thank you. How many ways? 6. Did I repeat a letter? No. Good. Question? Huh? Oh. All right, so grand total, how many different ways can I get from home to work? How many? You add them, right? So 15. 15 different ways of getting from A to B. No, you don't want to multiply them. You add them up, okay? So sometimes things are additive, sometimes things are multiplicative, okay? Now, let's say you have, and this is a great example, that's why I want to bring it in. Ooh. Here's a good one. How many 3-digit numbers can be formed using 2, 3, 4, 5, and 6? A, okay, 2 problems. Using each only once. And B, using each, oops, as many times as you like. So for example, 222 would be a solution in B, but not in A. Hmm? Well, sometimes if you're lost on this, when you're dealing with a small set, okay, you can usually begin to figure out how to approach the the problem by looking and saying, all right, let's do a few. Okay, so actually, well, first of all, what about A? Let's look at A. I mean, using each one once. That's a lot like my buffet example, right? And in that case, does order matter? 2, 3, 4 is different than 4, 3, 2, right? Does. Yes, yeah, right. If I'm making a number, I think if I'm making a 3-digit number, the order certainly matters. So in this case, we are dealing with permutation. So compute that beast first. What? I don't understand. Are you talking about part B? Or are you talking about part A? Part A, I have a buffet of 5 numbers, and I can pick 3 and make a number out of it. So in that case, if I choose 2, 3, and 4, I can choose them 2, 3, 4. I can choose them 3, 4, 2, 4, 3, 2, 4, 2, 3, so on and so forth. So in that case, it's a permutation because order certainly does matter.
Right. No, I think you were asking the same thing that I did before with the summation. So.
But I'm saying specifically 3-digit numbers.
Okay. So.
No. But we are going to have to fool with that in part B.
Wait. Part B.
We'll deal with part B in a minute.
But it's still 3-digit numbers. It's just you're using the numbers.
Wait. Let's just get there first. Get through A. Got A? Okay, good. It's 30. It's 30. No. No. I was answering his question. So 5 choose 3. That's 5 factorial all over 2 factorial, which is 5 times 4 times 3. So how many? 60. Good. Good. Now, with part B, let's look at this a little bit differently. In a problem like this where you're scratching your head and you're wondering just how to play this game, draw out some lines, start filling in some numbers. If I have 2, 3, 4, 5, and 6, and I have to choose 3 items, okay? How many choices do I have for the first space? 5. Good. How many choices do I have for the second space? I can use them any amount of times as I want. So let's just say I pick 2 for my first space, right? I can still pick 2 here. So I again have 5. And for the third, 5. So 125 ways of making a number. Okay? That fly? Good. Now, what if I said something like, you have to put the number 4 in there. The number must contain the number 4. Okay? Now I'm limiting it. Now I'm restricting it. All right. Different ways of playing this. You could first, well, let's first compute it using dashes, because that's very grounded and concrete. How many can I choose for my, no wait, let's go back to only being able to do it one letter at a time, okay? Must contain 4. a digit gets one appearance. All right? So I can't do 2, 2, 4. That wouldn't fly, right? Okay. Now, the 4 has to live somewhere. Okay? He could live in the first space, the second space, or the third space, but he has to live there. So let's deal with the 4 living in the beginning. How many choices do I have now for here? If I can only use a letter once. I've already used up my 4. I've only got 4 left to play with. All right? And now how many do I have here? 3. Okay? Now, this is when the 4 lived in the beginning. What happens when 4 lives in the middle? Oops. We'll have something like that, won't we? Yeah? And this gave me 12. This gave me 12. And of course, the third case will give me 12 also. Okay, so sometimes when you're dealing with a small set, it's easier to actually draw out spaces and solve it this way, okay? And even if it is a big set, sometimes you only really have to go into this method for a few steps before you realize, oh, okay, it's going to be do this and then add them all up at the end, okay? Now, let's ask that same question, but now you can use a letter as many times as you want. How many spaces now? How many choices go into this guy now? 5, because I could use the 4 again. And here, 5 again. So now how many will the whole problem contain? The whole final answer to the question. 75. See, because this is going to give me 25. And then the next one, does that make sense? Does that fly? Hmm? I'm telling, yeah. Yeah, I'm forcing the number 4 to be in my number. Yeah, in this, if I'm allowing myself to have any number repeated any number of times, but 4 has to be in my number, okay? 4 must be there, here or there. How to choose these numbers?
No, when you multiply it,
Right.
you get like 25.
Mm-hmm. Because this, yeah, basically, because this is forced. This isn't a number of items in a sense. This is, yeah, that's like saying, you know, like Dolly must be on the basketball team, and how many other people can be? Well, we still have 4 more positions to fill. Right? There are 5 people on a basketball team, right?
On the court.
On the court, good enough. Yes.
So for B, you got 1.5, right?
For this, using each as many as you'd like, was this. I had 5 choices for the first number, and then I can choose 5 here again because I can use any number in that spot.
What would you plug in for the total?
You wouldn't, in a sense, because that isn't a permutation or a combination. That's basically saying, how many paths are there in a sense, It's not, it would just be 5 cubed. There are 5 choices. Drink of water? You need a drink of water? Do you need a drink of water? Mr. Sandman's visiting you in that corner over there. Why don't you go get some blood flowing? Go get a drink of water. You look like he was slipping away from you there. All right. Okay. Yeah, we have only about 10 more minutes left. Okay. Here's a good one. I got 9 boxes labeled with the numbers 1 through 9. Okay. And there are 5 people. And everyone's allowed to take a box. But the first 3 people choose even numbered boxes. How many different ways can this be done? Draw out some lines. You got 5 spaces to fill. Five spaces to fill. Give us a chance. No, it's all right. I'll let you go. And now decide how many choices there are in each of those places.
I think for 3 people to get, can't the other 2 then take an even number as well, like fill up?
Well, how many even numbers are going to be left?
No, it's 1.
1.
Oh, sorry, no, I was saying, I think, is it 30?
Oh, I'd have to crunch it. Yeah.
So, like, you have, like, 3 people choosing the even boxes, and
Yeah.
then, like, with the spaces, can those people...
They can pick anything they like, whatever's left.
But, like, that's...
Okay, like,
They have, like, 8?
well, okay, here we go. 1, 2, 3, 4, 5. Sorry, Charlie. Okay. All right. She loves even numbers. She loves even numbers. You love even numbers. They don't have a preference. Okay. So there we go. All right, there we go. So how many choices does she have? She has 4 choices, right? 2, 4, 6, and 8. Okay. How many does Bailey have? How many does she have? She has only 3 numbers left to pick from. Okay. And then how many choices do you have? You have only 2. Okay. Now Nikki has to deal with whatever the heck is left over. So let's just say that Amanda took 2, Bailey took 4, you took 6. Okay? So now how many does Nikki have to choose from? She has all the ones that are left over. So she can pick up to 6 items, okay? Because she likes odd numbers as much as evens. And then Eric has how many to choose from? 5. So yeah, 720. Yeah. Do you see how we came up with these numbers? They don't have to be odds. They could just pick anything.
But if it was that case where they had to pick odd,
If they had to pick odds, then no one's choosing 8, right?
Yeah.
That's going to be left over for the rats, okay? So now we have 1, 2, 3, 4, 5 items to pick from, and then 1 is left, and then 4 is to choose from, okay? Okay. Question? Oh, okay, no, sorry. All right. All right. How many 3-digit numbers can be made using okay. Oh, I'm sorry, and 8. At most once each. If they must be even and greater than 300. And they must be 3 digits. Well, that's obvious. But only 3 digits only. No, it's a 3-digit number. It's an even 3-digit number that's bigger than 300. No, at most once each. Time flies when you're having fun. Expect a homework assignment posted within the next 24 hours. I'm computing it right now. This episode of the Ronco Show has been brought to you by Permutations and Combinations in the letter 4.